So, good evening, everyone. I'm Calvin Joseph, and today I'll conduct your summary session for the course, Control and Tuning Methods in Switch Mode Power Converters. So, we have gone through this entire long 12 weeks of NPTEL course, and we have reached the end. And so, you'll have to prepare for your exams. Okay, so this is what is the outline of your course, where you have learned a lot of things. You've been taught about modulation techniques, you've been taught about control techniques, then certain methods we use to model our converter. Like how do we analyze it? So to analyze it, we prepare a model that we have learned. Then to actually run our hardware, we need a controller to run it in closed loop. So how do we design the controller? Then certain aspects were taught about trajectory-based design, and then time optimal control also was taught. Okay. So what I want you to remember is like these are some basic points which you must keep in mind. Is you have designed a converter for steady state. Okay, you design it some inductance, capacitance, you have current ripple, you have peak ripple. Okay, so there are different criteria is there. Okay, so let me just start with the notes. It will be better like that. Okay. So summary session. One is the steady state behavior. Okay. So like either buck, boost, anything of those sort, you will have some ripple. Like this is your current, you have a ripple. Okay. Now, this is the time. This is your on time. This is your, okay, let me say this is your T on. This is your T off. Right? This is your T on again. This is your T off. So in steady state, we want the current to look like this. This is how the current will look like once it reaches steady state. So when it has reached steady state, your on time, off time will reach certain fixed value. There will be certain fixed value. So this has some average. Let me draw the average. Okay, like this is your average current. And this is your delta IL. Okay, your current ripple. So you have to, let us say, you will have to design the inductance, the L. L is designed based on your B input range, your output voltage range, etc. Your switching frequency and all. Right? So you have your, let us say for your buck or for your boost, this is your boost, your Q bar, this is your capacitor, load resistance L, right? Your input voltage will have a range. Your output voltage also will have a range. And based on that, you have to find the steady state. So to find steady state, what you have done, could you guys let me know how do I determine what is my steady state operating point? Anyone can tell me? I think we did it yesterday itself, right? What did we do?
By using inductor volt second balance and
Yes.
capacitor charge balance,
Yes.
we can derive it steps.
Good. So you will have to do what is known as volt second balance. Volt second balance you do for the inductor. That is the voltage applied across the inductor in one switching period is zero, the average voltage. Similarly, you have your capacitor charge balance. That is the average charge or the average current flowing through your capacitor in steady state for a switching period is zero. Okay, so these are certain concepts which you need to remember and you need to keep it in mind, right? So, so what sort of questions are asked? Does anyone remember what type of questions are asked regarding this? Because you have done 12 weeks assignments. You just recall what all questions are asked in your assignments, everything. Okay, assignment questions are very important. You must prepare them. You have been given the solution also, so go through it very, very carefully. Know those questions, all those questions very well. Okay, so can you tell me what sort of questions have been asked regarding your design? If you recall anything, what do you recall?
Sir, are you asking about the type of questions like multiple choice
Yes.
question, true
No,
or
no, no,
false?
not multiple choice questions. You have numeric answer type questions. You have select the right options. Also, you have. But I am asking regarding this topic, what questions were asked?
Steady state operating point, IL and
Mhm.
VC with and
Mhm.
without this parasitics.
Okay, so your IL
Then duty
average,
ratio.
VC average. Okay, you have to compute your duty ratio next. You could also have a question regarding RMS, root mean square. RMS, sir had taught if you have this quantity, you have suppose this waveform, you have x1, x2, x3, right? This is for T1, T2, right? So how do we get x RMS square is equal to 1 by 3 x1 square plus x1 x2 plus x2 square into T1 and and plus x2 square plus x2 into x3 plus x3 square into T2, the whole divided by T. Okay, it's not neat. Let me write it neatly again. Your x RMS square is equal to 1 by 3. There's a factor of 1 by 3 divided by the time period, that is your total time T, into x1 square plus x1 into x2 plus x2 square into T1. Okay. Then for the next section, for this section, it would be x2 square plus x2 into x3 plus x3 square into T2. So this is the formula for your RMS. RMS question can be asked for your inductor current. You can find the RMS question also can come. Okay. Then what are the questions they ask commonly is your inductance. Inductance design. How do you design the value of inductor for a boost converter, buck converter, etc.? Your capacitance design, right? This is based on your percentage voltage ripple, right? Then any other questions which are coming into your mind? Because the purpose of this session is to like give you an overview of what you have studied so that you are better prepared. Like it's a revision sort of thing, right? One more question is there is reluctance capacitance. Else is asked.
If the operating point is given, whether the converter is in CCM or DCM.
Yes. Good one. That we did last time also. So CCM or DCM mode of operation. So for this, you have to get the RC, the critical resistance. Okay. If the load resistance is more than RC, then it will be operating in DCM. So that means if R is greater than RC, it means DCM operation. If R is less than RC, it means CCM operation. Okay. This is good. Now, I have one question. You have a boost converter, assume. You have some input voltage, you have some output voltage. Let us take some numbers. Let us say your input voltage is between 10 to 20. Okay. Your output voltage, let us say it is 30 volt. You want to maintain your output voltage at 30 volt. So now, under which condition your delta IL is maximum? At which input voltage will your delta IL be maximum?
For a 0.5 duty ratio.
Yes. So it happens at D equal to 0.5. Any doubts in this? Because you're sure, right? Yeah, this is true. Because we know your delta L is what? It is V in upon L into D into your T. This is your on time and this is your on time slope. So V in we can write it as V ref into 1 minus D into D upon L into your FSW. Because your time period, your inverse of your time period is your switching frequency. Now, what happens? Your VREF, L, FSW, they are all fixed. But the thing which varies is your 1 minus D into D. And this product 1 minus D into D, if you recall what you have to do, you have to take the derivative and set that derivative to 0. And that value of D is the point at which your magnitude is maximum. Okay, you have to take the first derivative and the second derivative, etc. Okay, so it is known that that value will be D equal to 0.5, at which your current ripple is the maximum. Okay, so in the question also they have asked in the assignment questions also that your maximum current ripple can be this much, and your input voltage range is like this, right? So based on that, you can make the calculations. Well, what should be the inductance? What should be the input voltage? From that input voltage, you can get your output voltage, everything. Okay, the various things are there. So this type of question also was there in your assignment. Next, what are the questions you have? Your output voltage ripple for a boost is equal to minus I naught by C into your on time. So you neglect the sign. That will be V naught upon R C into D into T. Okay. So your delta V naught is V naught into D into upon RC into FSW. So if you observe, right, your V naught usually is regulated. You want your V naught to be regulated. So it is fixed. And if in your control technique, your FSW is fixed, then good. Otherwise, if it varies, if it is variable frequency, accordingly, you have to take that into consideration. Similarly, your C also is fixed, right? So your delta V naught is dependent mostly on D and C. Okay? Sorry, D and R. So if your duty is more, your delta V naught will increase. If your R is less, then your delta V naught will increase. R is less means what? Your load is more, means your current is more, that means your load is more, and your ripple will increase. And if your duty D is more, also then also your voltage ripple will increase. Okay, so these kind of questions also you would have come across. That you, if all these things are constant and you are given a range of input, output, input voltage, etc., that means you have to find your duty, maximum duty which is there in that range, and that you should consider in your solution, in your solving the problem. Okay? Okay. Then any other question which comes to mind? Okay. Let's proceed further. Volt second we have taught, charge balance also we have seen. Modulation technique, okay, we'll see modulation technique. We'll go proceed. What is this? Modeling technique, controller design. Okay. Okay, I have not included modulation technique. I'll talk a little bit about modulation technique. Okay. So you have two types of control. You have voltage mode control and current mode control. Okay. In voltage mode control, what do we do? We have a reference. We subtract it from our output. We get an error that we pass it to our controller that will generate some beacon which goes through our modulator that generates the duty which goes to our converter and that generates our V output which is fed back. Okay. So in voltage mode control, what do we have? Like we have this sort of array. We have this sort of RAM. Right? This is our sort of RAM. And this is our VCon. Okay, this is our VCon and this is our RAM. So this is what will generate your duty. This is what is generating your duty, your Q, gate signal Q, and this is your D into T, and this entire period is your time period T. Okay. So in this control technique, you observe that it will all of them will turn on at fixed intervals of time. It turns on at fixed intervals of time. But what is changing dependent on your control is the time when it switches off. The instant when it switches off, that is control. That is your falling edge. Means it is falling. This thing is varying, right? This thing changes depending on your VCon. So that's why this type of technique is known by the term that is trailing edge modulation. Does this ring bells? Have you heard this before?
Yes, sir. Trailing edge and leading edge.
Yes, yes. Trailing edge and leading edge modulation. Okay. So this is voltage mode control. It is the control. How are we controlling? What are we exactly controlling? We are controlling the voltage. And modulation is how are we using that Vcon to generate a gate signal. It can be done using trailing edge modulation. It can be done also leading edge modulation. Both cases are there. Okay. For VMC, mostly we consider trailing edge modulation. And I'll assume that you would get something similar also. Like questions also we basically ask on trailing edge modulation. Let's hope that's the way. Right. So this is voltage mode control. Now, sorry, let us see about current mode control. Any doubts still here? If you have any doubt, you can stop and ask me. Because you could have some doubts. If you have any queries, doubts, you can stop and ask me. Next is you have is your current mode control. This is a two loop control, or also known as cascaded control. Okay. Let us try to understand how this happens. First of all, this is a single loop. There is only one loop. So this is like a single loop control. Now we have to go for current mode control. So how do we draw current mode control is here also you have your reference. Your reference will be there in voltage mode control, current mode control, both cases, because your main focus is you want to maintain your output voltage at some fixed desired value, right? So that is known as your reference. With a reference, we compare our output voltage. That will generate an error. Based on that error, again we have a controller. This controller will generate what is known as our IREF in this case. It generates our IREF. Okay. Now, once it generates this IREF, when your IREF becomes less than your IL, okay, we compare it with our inductor current. Okay. And then that generates our duty, which goes to our converter, which in turn has some output voltage, has some inductor current. That inductor current information we feed back over here. This output voltage information we feed back over here. So this is our inner loop L1. This is our outer loop L2. Okay. So you have an inner loop, you have an outer loop, where your L1 is much faster and your L2 is the slower outer loop. Okay. Now, how do we implement current mode control? Like I have shown this diagram. I'm just trying to, revive these things which you have heard long ago about current mode control, voltage mode control. This is, the block diagram architecture of them. So we have drawn it. Now let us see how do the waveforms look under current mode control. So you have what is your known as your reference. Okay. Then you are comparing with your current. Current reaches here, it falls, rises, falls, rises, falls, rises, falls. Your gate signal Q, which you generate, is like this. Like this, like this, like this, like this. Okay, this is your gate signal Q. Again, I'd like to point out that it is all turning on at fixed intervals of time t. After time t, it will be turned on. But the point when it is turned off is given when it touches your peak, your reference peak reference. This is the time when it turns off. So again, what is being controlled? The instant at which your gate signal is being turned off, that is being controlled. So this also is known as trailing edge modulation. So this also is known as trailing edge modulation. Okay. Till here, what I'm trying to correlate is how you are actually using the actual inductor current to make the comparison. Whereas in the previous case, you are just using some ramp which you are generating, you're using. But in current mode control, you're using the actual ramp-like behavior of your converter, of your inductor current. You're using that for comparison. Okay, so that's why this is known as current mode control. Now, there is an issue. What happens when your duty is greater than 0.5 is it will reach here, it will fall this much only. Then it will reach here, and then it will fall like this. Then again it will reach, again it will fall like this. So it is no longer what is known as periodic. It has what is known as subharmonic oscillations. So when your duty is greater than 0.5, you have subharmonic oscillations. So to overcome this subharmonic oscillations, what should we do? Any suggestions?
Keep the duty ratio below 0.5.
Okay, that is a good thing, but we always don't have that flexibility because you want your output voltage to be some value, but your input voltage can change. No? It can go up, it can go down. So at one stage, if your input voltage is quite high, your duty is less than 0.5. But if your input voltage goes very low, that means you have to increase the duty a lot so that you can reach that output voltage. So in that case, your duty may go above 0.5. Okay, so input voltage is not in our hand. That comes from a supply. So let us say we want to find a technique better than that. What else can we do?
That slope ramp compensation.
Yeah. So instead, what you have is you have your new reference. Let us say you have your, this is your new reference dash, and it actually has a kind of slope. It starts. It will have a slope. It will have a slope. Okay. So because of this slope, what it would do is, color. Your current, suppose it hits here, it will fall. Next time it would hit here, it will fall. Slowly, that thing of hitting fast will not happen. It would hit here and again it will fall. It would be like this. So depending on this slope minus MC of your RAM, the tendency for your converter current to go like this, go like this, go like this, suddenly high, then go very low, suddenly high, very low, that would reduce. Like it is kind of reducing that occurrence. We'll try to reduce that occurrence. So there is some value of the slope MC which you need to reduce this occurrence, and that there's a criteria, RAM compensation criteria, etc. What I don't think that has been asked in your assignment questions, everything. But what you should remember is your duty should be, if your duty is greater than 0.5, then your peak current mode control has subharmonic oscillations, right? So to overcome that, what is done is ramp compensation is used. Now, if you use ramp compensation, there is a drawback. Your ramp compensation slows down your system. Okay, your ramp compensation slows down your system. It means slows down your converter. Okay, so if you use a very large ramp, like if this ramp is so steep, very steep, then it will slow down. What will happen is when it slows down your system, your current mode control then behaves closely as voltage mode control. So we had gone through all that pain. We had added an additional sensor to sense inductor current. We had this extra logic we have, and through all that effort we did, such that we can go for current mode control. Current mode control has an advantage is it is more robust as compared to voltage mode control. So we did all this effort, and then we found that under peak current mode control, fixed frequency current mode control, at a certain duty range, it becomes unstable. And to overcome that, we have to use ramp compensation, which is slowing down your system and could almost lead to voltage mode control. So, what should we do? There's a technique is we can go for variable frequency current mode control. So can you tell what were the variable frequency current mode control techniques which you were introduced to?
Constant on time modulation, constant
Okay.
off time, and hysteresis current.
One is your constant on time. Second is your constant off time. Third is your hysteresis current mode control. Okay, so these current mode control techniques are there. Now, you have, how do we implement constant? So let me start with constant off time. Again, you have your reference. Okay. Now, current comes like this. Once it touches the peak, okay, you have your gate signal like this. Gate signal. Your gate signal will be off for a fixed duration. So, it will fall till that value. Again, it will start to rise. Again, when it touches your peak, your gate signal will go off. And again, it will be off. Sorry. For this fixed duration. Okay. So this, let me write down, this is your constant of time current mode control. Okay, this is your constant of time current mode control. Here, if you will notice, again what we are doing, we are actively controlling the peak. We are actively controlling the peak. And what is being controlled is the instant of turn off. Instant of turn off. That is being controlled, right? So this constant of time current mode control is analogous to peak current mode control. That it is equivalent. It is almost similar. They have lots of resemblance. But what happens is this time, this T1 and this T2. Your T1 doesn't need would not be equal to T2. So that's why it is known as variable frequency current mode control. Okay. So this is like your constant off time current mode control where we are controlling the peak. And this is useful for buck converter. For buck converter, this is quite useful. And it is used for battery applications where they want to have, accurate control on the current. Okay, so this is used for buck converters where you have this battery application and all. Okay. Now, this one doesn't have the constraint that if duty is greater than 0.5, it is unstable. This is not true. This is stable for the entire duty ratio range. From 0 to duty 1, it is stable. So that is the advantage that why we are going for variable frequency current mode control.
Sir,
Yes, tell them.
sir, actually, we got only assignment answers till 8th assignment, 8th week. Third answers.
Oh, you didn't get till week 12?
Solved answers till 8th only I received. I don't know whether others have received or not.
Okay, what about Arun?
Yes, sir. In that portal, till 8th only it is uploaded.
Okay, then you write a mail or in that forum or something. Previously, you did something, no, Parvati?
Yes, sir. I wrote a mail, and after that only it came. Now again I will let them know.
Yeah. Again, we let them know because this is very important for you guys. You need the assignment solutions, right? Yeah.
Sir.
Okay. So that you do. But you have submitted all the assignments, no, by today?
Yeah, yes, sir.
Okay. Okay. So now, so this variable frequency constant off time current mode control is stable. Next is you have what is known as your constant on time current mode control. Now what do we have? This is our reference. And current will fall like this. Then it will rise. So how will your gate signal be? Your gate signal will be like this. It was off, then it tried on. It is on for a fixed time, and then it is off. Okay. So for a fixed time, it will be on. It will reach here, and then it will be off. And once it touches the peak again, then what you do? Then again you turn on for a fixed duration. Okay. Your pulse will rise again, and then it will turn off. Okay. So what is being controlled here? Like you are changing the status depending on when it touches the valley. So this is like a valley control. You're controlling the valley of your current. Okay, it's like a valley control. And the instant when it is turned on, that depends when it will intersect with your valley reference. Okay. So that also you are controlling. So this is your constant on-time current mode control. Here also your duty, it is stable. It is stable for your entire duty cycle range for constant on-time control. But if you go for fixed frequency, valley current mode control, it is unstable for 0 to D to 0.5. It is unstable for this case. When your duty is between 0 to D to 0.5, it is unstable for fixed frequency valley current mode control. But when we go for variable frequency, that is by virtue of constant on-time current mode control, it is stable for the entire duty cycle range. So this is an advantage of constant on-time current mode control. Okay. Any doubts in this part?
Sir, what you told last, I didn't understand.
Okay.
Now, fixed frequency.
So here your frequency is T1. Here you would have another time period T2. So your T1 is not equal to T2. Okay, that's why this is variable frequency current mode control. But if you have fixed the frequency, and when you do fixed frequency valley current mode control, your T on will no longer be fixed. In such a scenario, it would be unstable for this range when your duty is between 0 to 0.5. Okay. And for fixed frequency peak current mode control, this is for peak current mode control. Duty is unstable. It is unstable for duty greater than 0.5. Whereas for your valley current mode control, it is unstable when your duty is less than 0.5. Okay. And this is for fixed frequency. I hope this is clear, or you want me to repeat it?
Yes, sir.
Okay. So this is, then there's a last technique which is left, which is your hysteresis current mode control. So what you have your peak reference, you have your valley reference, right? Your current, how it goes from here, reaches the peak, goes back down, reaches the peak, goes back down, like this. Okay. So one question you would have seen in the assignments is they would have asked you to calculate what is the time period. What is the time period? So what would be given is your band. What is your delta IL would be given to you. You have to find out what is your M1, what is your minus M2 slope of current. And these depend on your input voltage, output voltage, etc. And based on that, you will have to find your time period. Okay, this question also is asked. You have seen it, right? In your assignment question, you would have observed this. Okay. Now, after all this, so we have seen different sort of modulation techniques. We have considered. Next, you have your voltage mode control. And you have your current mode control. We have to model them, right? We have to model it. So for modeling, what do we do? We have your state space representation. This is one approach. Another is based on your circuit averaging. and perturbation. I had a very nice question I'd asked when I was doing in one of the weeks. So, what are the steps? Steps for modeling. One is construct the averaged dynamical model over the switching period T. Okay, that is over the switching period T. Next is we add a small signal perturbation. If you remember, we add for a duty D, we write it as D plus D perturb. Our output voltage we write as V output plus a V output perturb. This is what I'm talking about. Your inductor current, we write it as an average one plus your perturb one. Okay. This is how you write that. Then we separate the DC terms. So these DC terms will give you what is known as your operating point. They provide you with the information of your operating point. So from the operating point, you can see what affects the efficiency, where it will settle, which parasitic has which drop. All those you can get from your DC terms. Next is you have to gather and you have to separate the AC terms. This is your small signal model. And in this process, what you do, you ignore the second order product. That is, if you have IL perturb into D perturb, you approximate it to 0. Because you're considering that the perturbation of IL and D perturb are very, very small as compared to your average duty and your average IL. Okay, this is what you consider. Right? And based on that, then you generate the transfer functions. Okay. So this is the modeling approach which is done. And then you get your transfer functions. Any questions in this part? Okay. It's difficult, I know, but let us try to keep our heads in this. So you get 4 types of transfer functions you get, right? If you remember, one is your control to output transfer function, which is your GVD of S, which is your V output perturbed by your duty ratio perturbed. This is your GVD of S, control to output transfer function. That GVD of S is given by your KDC into 1 minus S upon omega RHP 1 plus S upon Q omega naught plus S square upon omega naught square, right? And yesterday we had an extensive discussion about this. For your buck converter, for your boost converter, what values you give. And a buck converter doesn't have this omega RHP, but your boost converter has this omega RHP. Okay. So this you can refer to yesterday's video where we extensively discussed how do we remember what is our KDC How do you remember what is our omega naught, Q omega naught, etc.? You can remember. So I hope you will go through it and learn this. This is important. GVD of S is there. So if I just write for a boost, that is given by V in 1 minus D square, 1 minus S R into 1 minus D square L upon 1 plus SL upon R into 1 minus D square plus S square NC upon 1 minus D square. If you will notice this transfer function, it is dependent on your V in. It is dependent on V in. So when your input changes, your transfer function also will change. When your duty changes also, it will change. But what I would like to stress is your voltage mode control is quite susceptible to changes in your input voltage. Right? It is dependent on V in. It is quite a lot dependent on V in and less dependent on your load. So that's why it has poor line regulation. Poor line regulation means when your input will fluctuate or changes, your output under this voltage mode control is susceptible to it. It is affected by it. Okay? It is affected. So to overcome this, you have to use input voltage feed forward can be used. Okay, input voltage feed forward can be considered. Okay, next is you have your GVG of S. This is known as your audio susceptibility. Transfer function, which is given by V output per turn of S by V in per turn of S. Okay, this is your GVG of S. Similarly, you add a transfer function, which is your Z output of S. That is given by minus of V output per turn of S by I output per turn of S. This is its transfer function. Okay. And finally, you had your Z in of S, which is your V in per turn of S by I input per turn of S. Okay. This Z output of S is for your load transient. To analyze the behavior when there is a load transient, we use Z output of S. Z input of S we use when we have to do impedance matching. And we have to do input filter design, right? And what else? When you have to do MPPT, all those cases, this Zn of S you will consider, the input impedance you consider. All right. Okay. Any queries in this or any points you think are very important? You want me to repeat it? You want me to stress on it? You want me to talk on it? You can let me know. Okay. Because this really is a very vast subject and you guys really have a very wide syllabus, I know. But I'm trying to let you know of the important things which you could refer to. Yeah. Then these are your transfer functions. So after this, let us see for current mode control. Yeah, these transfer functions are for voltage mode control, GVD of S and all for voltage mode control. Now in current mode control, what do? We set our control current reference to be approximately equal to by inductor current perturbation. When you do that, you will get a set of equations. I hope you remember you had some question where you have your IC per term is equal to A into your V output per term plus B into your B in per term plus C into your D per term or something like this. C into D per term or something. Okay. And then you add your V output per term is equal to F into input per term, output per term plus G into input per term plus E into D per term something. So you get some like this set of equations. Okay. And in current mode control, after you get the set of equations, you have to get your modulator gain. This is important. In one case, it comes out to be 1 upon MC plus M1 upon 2. Then in the next case, where you average it over your entire time period, it comes out to be 1 upon MCT. So these things also you should remember. These are important. Then, yeah, many things are there. What more do you recall? Also, you have to. Okay, you have got all this, right? For your current mode control, your transfer function is GVC of S, that is V output per term by IC per term of S, that is equal to 1 minus S upon omega RHP upon 1 plus S upon your omega pole into R by 2, where your omega RHP does not change. It still remains as R into 1 minus D square by L, and your omega pole becomes 2 upon RC. Okay. So now, if you notice this transfer function, you will understand that your omega RHP, you cannot change your omega RHP. Omega RHP will not change. Whether you do voltage mode control, current mode control, you cannot eliminate your omega RHP. It is present. Okay, it is present. So that is why it results in what is known as your non-minimum phase behavior. Okay? Okay, very good. Now, if you see this transfer function, it depends a lot on something, that is your R. Sorry. It depends on your R a lot. So that's why current mode control depends on your R, and your R will change a lot. So that is why current mode control has poor load transient performance. It has poor load transient performance. Okay. So because it has poor load transient performance, what is recommended is we use what is known as load feed forward. Load feed forward means we have to sense I output current as well, or we should estimate I output. This is meant by a load transient, for current mode control. Because current mode control depends on R, it is very, very susceptible to changes in your load R. That is why if you use load feed forward, we can improve the performance of current mode control. Okay. Now, if you notice, this is first order. It is like a first order transfer function. Whereas for your voltage mode control, it was a second order transfer function. So that is why current mode control is more easier to compensate. more easier for you to control it, for you to design the controller. Okay. So, what else do you recall? Let me check. So yeah, DC circuit averaging, voltage mode control modeling, current mode control modeling, state space representation is there. Okay, controller design. Controller design. Before that, I like to stress on this PID. PID controller. Sorry. If you increase your KP, your percentage overshoot will increase. Your settling time, it doesn't have that much of an impact. And your steady state error can reduce if you increase your KP. We had also seen a MATLAB demonstration. I think this was done in week 11, I think. Okay. Next, if you increase your KI, your percentage overshoot will increase, but you can get zero steady state error. That is the reason we use KI, an integrator. It will reduce your steady state error, it will eliminate it to zero. Next is you have your KD. KD is mainly used for your transient performance. How it does is it improves your damping. Since KD improves your damping, your percentage overshoot will reduce as well as your settling time will reduce. Okay. So this is your PID controller. And you have, so now basically we'll go for our controller. Now you have your one controller which you have is you have your PID controller. In this case, your GC of S should be KP plus KI by S plus KDS upon 1 plus tau S. Okay. Where, why do we need the tau? Can anyone tell me?
We cannot practically implement that ideal PID controller with infinite band
Yes,
limited
yes.
derivative in it.
Good, good, very good. So it is a band limited derivative. This is your band limited derivative. PI by S, this is mainly used for improving your it's for zero steady state error. And if you remember, sir had told it when you go for time optimal or large signal gains, large signal control, your KI is small and has negligible impact during the transient response. It has a negligible impact. Right? It has a negligible impact. Your KP, this is very important. Because when you see your phase plane, KP is the one which is setting your slope of your switching surface. KP is the one which is setting your slope of your switching surface. Okay. Where you, if you recall, we have talked about it that we are going from one operating point, we go here, and then we come back to our next operating point. Right? One operating point, next operating point. It turns on, turns off. This is your ideal time optimal control. So I'd like to reiterate, your KP is the one which sets your slope of your switching surface. Your KI is the one which is used for eliminating your bringing zero steady state error. KI is small, so in the transient response, it has negligible impact when we consider cases for time optimal control. KDS upon 1 plus tau s. That has which is a band limited derivative is there. We cannot have infinite bandwidth. It is not practically possible. As well as KD improves your damping. It increases your damping in your system. So that is the role of PID. Now, any other controller which you guys have come across? Which we have discussed about? Yesterday we discussed, right? We discussed about type. You have type compensator. You have type 3 compensator, etc. Okay. Where your GC of S is actually, there will be an integrator has to be there in your controller. That has to be there. Then you have a 1 plus S upon omega Z1. And this is 1 plus S upon omega P1. If this is your compensator, then this is a type 2 compensator. Now, if you add an additional 0, if this is an additional 0 is there, then it becomes a PID. And if you add an additional pole, it becomes a type 3 compensator. Okay. So this, kindly keep it in mind about this. And when you are doing your controller design, you are using your pole zero cancellation, right? Pole zero cancellation technique you are using, where you cancel your plant poles with your controller 0, you cancel your ESR 0, and various things you do. You cancel plant poles with controller 0, as well as you cancel the ESR 0 with the controller pole. You place one controller pole in coincidence with your RHP0, and also then you design your DC gain based on bandwidth and phase margin. Okay. These things you'll have to try some sums which we had done. Assignment sums are there, the recordings are there. You try some controller design. Controller design is important because we're doing control and tuning methods, where basically we are studying about designing a controller. So I'd advise you to go solve sums using your hand regarding this controller design and learn. And as we saw earlier, for an ideal boost, if you're doing voltage mode control, you know your KP will come out to be 0. That you keep in mind. Your KI depends on your DC gain. Using DC gain, you design it. And your KD, you get it from pole 0 cancellation. This is considering that your tau is equal to 1 upon omega RHP. Okay, these things important. Remember. Next is you have these aspects. What else was taught was phase plane. phase plane is, you have your inductor current, you have your output voltage. This is how your trajectory will look like in steady state. Right? Achha. Before this, let us see what is known as eigenvalue, eigenvector. You have your eigenvalue and eigenvector. So if you have a matrix A, let us say 1, 2, 0, 5. Can you tell me what are its eigenvalues?
1 and 5.
1 and 5. So is this system stable or unstable?
Unstable.
So this system is unstable. Okay. Suppose this is your x1 axis, this is your x2 axis. Then to go like this. Go like this. Something like this. Not from the equilibrium point. Suppose say at this point, it would increase much more in x2 as compared to x1 because x2 has the higher eigenvalue, x1 has a smaller eigenvalue. And how Arun could directly tell what are the eigenvalues is because this is an upper triangular matrix, so your eigenvalues are your diagonal elements. Okay, your eigenvalues are your diagonal elements. If it is not upper triangular, lower triangular, diagonal matrix, then you have to use your lambda I minus A. This mod is equal to 0. Apart from this, how do you find the eigenvector? What is the formula for that?
AV equal to lambda V. So lambda I minus
lambda V. Or you could use lambda I minus A into V bar is equal to 0. This will be 0 bar. It is a vector. Okay, this is another thing you have to find eigenvalues and eigenvector. Okay. We also studied for this is like this. If your eigenvalues, let us say, were -1, comma -3, right? And if this is what your initial condition. Sorry, this is x1, this is x2. So since -1 is for x1 axis, and -3 is for your x2 axis, to reduce in x2 much more as compared to x1. So the trajectory will look like this. Okay? Not like this. Let me draw better. It will come like this. It would lean like this. Let us consider a case where it is same, -1, comma -1. Then it would come like a straight line like this. If the case was it is -3, comma -1, -3, comma -1, then in x1 axis it will. No. If it is -3, comma -1, means in x1 it will fall much faster. So I'm sorry, this should be for that case. This your -3, comma -1, and this is your -1, comma -3 case. Okay. Any questions? This is also something important. If you have any doubts, you ask, because this is like a very easy question. You got it in your assignment. This is very easy to solve, right? Okay, the meeting will end in 1 minute. I will restart the meeting. Okay. So till this point, is it clear, or you want me to repeat anything? Parvati, Arun?
It is clear, sir.
Okay, okay. Parvati is not saying anything?
Yes, sir. It's clear.
Okay, okay, very good. So I'm hoping you both will be the toppers, hopefully.
Arun will be.
Okay, let's see. So we have studied your face plane behavior. Right. Now, what is important is you have, let us say you have a transfer function. It is given by 1 upon s square plus 2 zeta omega ns plus omega n square. And this is also omega n square in the numerator. Right? So for this transfer function, if you give a step input, your output will change like this. It would go a little bit different, or else it could be the case of critically damped, or else could be the over damped case. So all these depend on your zeta of your transfer function. Okay, if your zeta is less than 1, then you have this oscillatory behavior. If your zeta is equal to 1, then you have your critically damped behavior. And if your zeta is greater than 1, then you have your overdamped behavior. Okay. Now what will happen when you have a RHP? If you add an RHP, what would be the effect? What would be the problem?
In the beginning, there could be an undershoot.
Okay. So as we said, there would first be an undershoot and then it would rise. Okay. Some undershoot would be there. So this undershoot, what is the problem if this undershoot is there? What do you think? What would be the issue with that? Is it good? Is it bad?
If the load is sensitive, then there is that voltage undershoot is not admissible.
Okay. That is a good thing to say. It's correct. Also, what happens? Your controller will start taking action. And when your controller will say that your voltage has dipped, what it will do is it will increase your duty. Right? No. You are actually increasing your reference. But then what is happening? It is going the opposite direction. When it should actually increase at the start, it is reducing at the start. So that acts like a delay. It's kind of like a delay is added. And your omega RHP, what it does, it reduces your phase. It adds gain, but it reduces your phase. And that is actually not good, because when your phase is reduced, your phase margin will reduce. And your phase margin is linked to stability. Okay. Also, one easy type of question you have seen in the assignments. You have your plant that is given by some 2 upon, let us say, s plus 1 into s plus 2. What they're saying is you have to design a controller for this. GC of S. So that you will add, what you will do, your controller should have this much, it should have this. To cancel your plant poles, it should have an integrator. Then it could add 1 pole 1, 1 pole 2. This it can have. So now what would be your loop? So you have your reference, you have your controller, you have your plant, and you have your output. It comes over here. This is your error. So your loop L of S is GC of S into GP of S. Now, your closed loop transfer function is given by GC of S into GP of S upon 1 plus GC of S into GP of S. So that is equal to your loop L of S upon 1 plus L of S. Okay? Your loop is this L of S. Your loop. Now, your L of S is equal to GC of S into GP of S. So that is equal to 2 upon S plus omega P1 into S, right? Into S plus omega P2. Okay? Now your GCL of S, that is equal to your L of S upon 1 plus L of S. That is equal to your 2 upon S plus omega P1 into S plus omega P2, 1 plus 2 upon S into S plus omega P1 into S plus omega P2. So your G closed loop of S is equal to 2 upon S into S plus omega P1 into S plus omega P2 plus 2. Okay. So this equation, this is known as your characteristic equation. This is your characteristic equation. So there is something known as, you place your poles. Placing the poles or designing your controller. What you do is, what they tell is, you have to make it behave like second order. If you will observe this transfer function, is it second order or third order? What is the order of this transfer function?
Third order.
Okay, it is third order. So it can be simplified into something like 2 upon S square zeta omega ns plus omega n square into your S plus omega P. So what is done is, your omega P is placed greater than 10 into zeta omega n. Okay. That is, the pole is placed 10 times more than these poles real part. Okay. Just hold on, I'll drink water. Okay. So it is placed 10 times more than the real part of your second order poles, so that it would behave to be like a second order dominant response. So this sort of question also could be asked. Okay. So any doubts till now? Any queries? Because I know this is a very vast subject, very vast course. I have tried to provide the recap till now. If you have any topics in which you have doubts, you want some clarification, you need any further explanation, you can ask it. Okay.
This one is clear, sir.
Okay, this is clear. Then you have in your time optimal control, you should buy out the formulas for peak current, delta V voltage undershoot, your recovery time. This you have to do for your load transient change, and for your reference voltage transient change. For both, you should keep it in mind. Try to buy out the formulas. Another thing is, you have your characteristic impedance ZC, which is equal to square root of L upon C. So, like it is known as characteristic impedance. So, what is its significance is, based on your values of L and C, these govern what is the possible achievable recovery time, what is your peak current, what is your voltage undershoot, etc. This is dependent on L and C. So your characteristic impedance is an important thing for you to remember. And this has something square root of D into I naught, various things. It is different for step up, step down. All these things I recommend you learn it. This is important for buck converter. For buck converter and all, you have observed, right? So this is for your time optimal control. Another thing is, you have what is known as your light load operation, where it sometimes functions in DCM. So for this case, in light load, what do we want to do is, we want to reduce your switching frequency. If you reduce your switching frequency, what you are effectively reducing? You are reducing your switching losses. So to do that, one technique that is known as your constant on-time control is very useful. When constant on-time control operates in DCM, then what do you see? Your switching frequency is proportional to your load current. So if your load current will reduce, your switching frequency also will reduce. And if your switching frequency reduces, your losses also will reduce. Okay, so this is there. There are certain formulas for constant on-time control that also you keep in mind. And what else? Any other things? Which you want me to touch upon? Provide you some things to learn. Because you have many things you have to study. I'd suggest you keep notes and write down very important formulas. Read it. Read those important formulas just before going to bed. Every day you have time till 2nd of November. So today is 15th October. You have half a month. So important formulas, you write it down. Write it down somewhere. And before going to bed, read those formulas. Okay, you will not recollect it every time, but read it, close the page, try to recollect how much you remember, go to bed. Again, next day you do it. Slowly, by the time you give your exam, all the formulas you know it very well. You should know it very well. This is the technique you guys would have used also for your GATE exam, for JEE, common entrance exams. This is the way we do. Read the formulas multiple times such that it is firmly fixed in your head, right? That is one thing. RMS things also you know. And certain questions are tricky. When tricky questions come in the exam, don't waste all your time, energy on that. Solve the easy questions. You have the option to go back and forth in NPTEL exam, I assume. Between the questions, yeah, you have the option. So that's why you solve the easy questions first. Make sure you get it right. And then you go to the next question. And do you have negative marking in NPTEL?
No, sir, no.
Okay, very good. So you don't have negative marking. And yeah, try to get the answer not considering parasitics, and then you closely approximate to a possible answer. And be careful with your calculators and calculations. As much as possible, I'd recommend you to get it into some kind of parametric form. Like in this expression, something you don't directly substitute the values and do. You find the expression, you find these expressions, and then you substitute the values. If you know the expressions by heart, you don't need to find it. But in case you don't know, you can also derive it during the exam time as well. Like that. And okay, what else? What is your like general feedback of the course? Is it useful for you, or it is very difficult, or what do you think? Like what changes should we do? Not changes also, whether the good points also you can tell us, whether the bad points also you can let me know. Or whether hard things are there, all that you can let me know.
This course was very useful, sir. I think for anyone working in DC converters, this will be very beneficial.
Okay. Yeah.
Because there are many other courses in NPTEL, like fundamental power electronics courses, but this control part and this transfer function, all those things are not there.
Okay. Yeah. Yeah. That's true. And since you and Parvati both are working on DC-DC, it is much very well aligned for your research. Yeah.
Live sessions were very useful, sir.
Okay. Thank you. Thank you. Yeah. It's good you guys joined also. Then what about the assignments and all? How do you find the assignments?
Very difficult, sir.
Sure. You're finding assignments very difficult, exam also will be difficult. So try to reach a stage.
Some assignments were easy, but some were little difficult.
Yeah. Mhm. Yeah. Okay, so Parvati, you have to send that mail to ask for the assignment solutions.
Okay,
Because
sir.
that is important for everyone. Okay. Then apart from that, what are your exam centers which you have received?
Sir, I didn't receive the hall ticket till now. Any center, any information?
Why? Even Arun, you have not received?
No, sir. Usually, only 1 week before the exam, they usually send the hall ticket.
Oh, but then what if you have to travel?
No, usually we get nearby, near in our hometown only. In my case, all the previous exams were only in the nearby location.
Okay. Oh. Hmm. And usually, what is the timing for NPTEL exams?
Sir, there are forenoon sessions and afternoon sessions. Forenoon, it is 9 to 12.
Okay.
Then afternoon, 1 to 4, like that. 3 hours duration.
Okay. Hmm. Yeah.
This is my first NPTEL exam, sir. Oh, I don't know much about that.
Yeah. Don't worry. So you're giving only one NPTEL exam or you're giving two?
One NPTEL and one self-study and one MTech course.
Okay. Yeah. Right. So all the best. Mm. Let us know how it goes, exam, everything, and how much time do they take to announce the results? What is the delay gap?
Sir, usually after within 2 to 3 weeks after the exam.
Okay. Because your this marks also gets carried into your main mark sheet for your semester, right? So that also has to come by that time, no?
Yes, sir. Yes.
Okay. Okay, you can ask any question or else then I think Tata bye for this course. It's very good. Thank you for joining. It's very useful. Your questions are very insightful. It helps me understand more of what I'm teaching as well. Yeah, and many times you have found me making mistakes also. It's very good you corrected. So I'm very happy about that. Yeah. So I enjoyed teaching. 2 hours is quite hectic, I'll admit. Yeah. So today, like I've got tired. I'm drained out. Since summarizing such a heavy subject, it has lots of things. There are certain things which I couldn't summarize as well. But I hope you'll be able to go through it and do the exam well. Yeah. Okay. So once again, I'll iterate. Assignments are very important. Solve the assignments very well. Be very thorough with the assignments. Yeah, you were saying something?
Hi, sir. Thank you for all your sessions. All the sessions were very useful.
Yeah, very happy to hear
To help.
Yeah.
In my case, in the previous semester also, in that state space approach, you were the TA.
Yeah.
So actually, since I am attending doing part-time research, there is no teacher from the institute side. All the courses are NPTEL. So I feel like you are one teacher. Because only in this case, a live interaction is there.
What about the other subjects, NPTEL subjects?
In the previous semester, I took advanced power electronics by Dr. Feem Singh. In that case, in that course, there was no live session.
Oh, okay. Oh, sure. So you had to take only 3 courses, not 4.
Four courses. In the previous semester, 2, and now 2 courses.
Okay.
And another course is wide bandgap devices. And there is a live session, but
Okay.
but both sessions are on the same day. So I joined on this course because this was more difficult compared to that course.
You had mentioned wide bandgap devices. Yeah. But I forgot which professor for wide bandgap devices.
That is Maumida Das, Dr. Maumida Das from IIT Mandi.
Okay. Yeah. Okay, very good. So all the best for your upcoming research, and hopefully maybe we could meet probably in some conference or something. Who knows? Let's see. Yeah. Good. Okay, then we can end the meeting. Thank you for joining. All the best for your exams. Yeah.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.